thank you to everybody who's here in person and everybody who's dialed in online. We're excited to talk about some spectroscopy, and thank you very much to Tom Field from RSpec to coming out and presenting with us. Just a little bit of a background on Tom. Tom was a contributed editor at Sky and Telescope magazine for 10 years. He is the founder of Field Tested Systems and the author of RSpec software, which I'm sure we'll go over a little bit today. RSpec received a Sky and Telescope Hot Product Award. He is a pioneer in the field of amateur astronomical spectroscopy, and he aims to demystify the field and make it more accessible to all. And he promises to open the door to this fascinating field. So without no further ado, Tom Field.
Thanks so much, everybody, for coming tonight. And Matthew, thank you for all the arrangements that we went through. He's like the hero behind the scenes. I think sometimes we don't appreciate how much work goes into making events like this happen, getting people in, getting, just all the scheduling and so forth. So thanks very much, Matthew. I'm sure everybody appreciates that. I've given this talk quite a few times, and sometimes I think I ought to just, when I'm in person, and I've given it at the Star Party down there in Florida Keys and other places, Okie-Tex last year. Sometimes I think I ought to just pull up a seat, like sit on the table with my legs swinging and just have a chat. And I'm not going to do that, but I wanted to start by mentioning that because what I'm going to show you is something that I love dearly. And like anything, whether it's your child or your latest astronomical photo or the skies that you're showing people, we like to share those things that are beautiful and have brought us a good experience, enrichment in some ways. So yeah, I'm a small business. I sell product, but really what I'm selling you is that there's so much that we can learn so easily to deepen our experience of the skies. And I'll get into that as we go through my talk. You'll get tired of hearing me say that. So let's get started. Of course, this is our iconic pillars image. And sometimes I think to myself, what about all these stars out here? Don't they sort of feel like they're not getting any limelight, that they're, all the attention's going to the pillars? Every one of those stories, every one of those stars has a story, right? And I've honestly was interested in that. I wanted to know what's up with all this. Now, my background is I'm a knuckle dragger. I'm a programmer. I've been programming for almost a half a century now, literally more than a half a century. And seniority doesn't mean much. Meritocracy is where it's at. So after I'd done a fair amount of imaging and other observing, I wanted to understand a little bit more about the stars. But for me, it was really intimidating. I was worried that I'd, have to have an advanced degree and there'd be a lot of math. And what I'm going to show you tonight, I hope you'll appreciate, doesn't have any of those prerequisites. So we all are standing on the shoulders of giants, of course, and we're going to cover some of that ground tonight. If I was here, I would be probably on the backside of this tower facing the wrong way. It's the first time I've said that, but it's true. There's no doubt people listening to this talk know far more about the stars than I do. But I hope to show you some things. Now, if you're not a telescope person, if maybe you're just an appreciator of the skies, I think you'll get a lot out of this presentation too, because, about 80% of the knowledge that we have about stars, their life cycles, supernovae, come from spectroscopy. So if you never do it yourself, it's still something that I think you'll appreciate and gain some value out. So how can we learn more about the stars that we love? These days, it's like drinking from a fire hose, right? And that's really probably the biggest challenge I think many of us face is, where do I start? Where's something at my level? Well, I'm going to show you mostly examples tonight and talk a little bit about how you can capture them. What I found is that when it's your own data that you're looking at, you have a much bigger commitment to it and much more interested in diving into Google or AI or however you're doing your learning these days to learn about it. We'll see a little bit more of that as we go forward. Just a quick example to get us started here, our beloved Orion's belt. There are the three belt stars, and you can see over on the right the three stars have their own specific spectra. We're going to talk about these rainbows, how we produce them, and then look at how we can examine them to learn so much more about the stars. It's incredible how much we can learn. So, and it's not that it's something that's incredible to somebody who hasn't learned it yet. It keeps on being incredible that this light, that light coming to you to your telescope, maybe even tonight of Vega, if we tease it apart, there's so much information there. So another quick example, this is a star field in Perseus, and there's the star field, and that was captured by a DSLR. Now, these three stars are what we're going to look at because, in fact, the entire star field is pretty boring, right? It's a bunch of dots. Who cares, right? A couple asterisms here and there, but enough is enough. I want to see faint fuzzies or craters on the moon. I want to see something interesting. Well, this is interesting if we delve into the details. So here's the same image captured with a very inexpensive filter, $200 filter called the Star Analyzer. Let's take a look at the results. Now, this is with just a DSLR. So the first point I want to make is you don't need big aperture. You don't need dark skies. Small aperture, urban skies are enough. So the first thing we want to look at here is let's look at this star. And we can see its spectrum is over there, right? And if we look at that rainbow, we can see there's some, well, apparent gaps. It's hard to see visually. And that's why we use software to unveil those gaps and study them. Just a quick bit of science, just to get everybody to the same level. We'll dip occasionally into the science, but there's not a lot required to get started. And that is each element has its own spectrum fingerprint. We'll talk about where those lines come from a little later. But for now, let's look at this star and see what it's all about. So, quick story here. Probably 15 years ago, my wife was going on an errand with her Garmin in the car. That dates the story, right? And she got to it was some strip mall that she'd never been to. And she got there. And when she got back in the car after she'd gone into the store, she didn't turn her Garmin on and she went to leave and she didn't know which way to turn. So maps are really helpful to us, right? And so what I'm going to show you here is a map that helps us compartmentalize our understanding of the stars. Some of you will be familiar with the HR diagram, but really it's very quick to talk about, and that is we have a temperature scale here. For historic reasons, the hotter range is over here on the right and the cooler range is over on the left. Now that star we were just looking at from its spectrum, and we'll see a little bit more in a moment about it, is a cool type M star. It's very red. So if we expand this map to a second dimension, we can see what's called the HR diagram. We're not going to get into a lot of detail at all, except to point out that, let's see, there's Vega. So Vega is a type A star, and that's how bright it is. This is a brightness scale here. And the star we're looking at is like Betelgeuse, right? It's above this M. It's a cool star. So most stars live their lives most of the time on this curve right here, on this line. But that's all I want to show you for now about that HR diagram. So this is a type M star, and we located it using that temperature scale and the spectrum. So what about this star here? It doesn't have those gaps, right? It's got one bright spot. And those bright spots indicate that it's a type BE star. B is a hotter star, and the E stands for the fact that it's got a circumstellar disk of dust. So if you've got anything bigger than a DSLR or a 4-inch telescope, could detect this bright emission. It's the glowing disk, and you can tease that out of the light. So where's that star show up? Again, it's a B star, and we'll talk more about how we locate stars on here, how we find them. It's somewhere up in this region here. Last example here in this set of examples is this bottom star here. You can see lots of bright spots in its spectrum. It's brighter yellow, brighter red, and so forth. This is what's called a Wolf-Rayet star. It's a late stage star, The outer shells have dissipated. All sorts of elements in the interior of the star from the fusion furnace are showing up. We're not going to read all this, but what happens is once you capture a spectrum of a Wolf-Rayet star with your own gear, then you come to a site like this and you read it, and more importantly, you remember it because it's your own data. So Wolf-Rayet stars are really hot stars. So they would be, just to move on here, they would be somewhere like up here, right? They're an O star, increasing temperature, maybe even over here. So that's the kind of thing that we can do with spectroscopy. Now, I mentioned earlier this little grating. It's an 1.25" grating, and it's got what's called a diffraction grating inside of it. It's just like a prism. It just splits the light into a rainbow. And to show you it operating, I'm going to stop sharing my screen for a second if I can find the spot. So maybe I'll be a little bit bigger on your display. Maybe not, Matthew. And then I've got this gas tube here. It's plugged into the wall. You can see it's glowing. And I'm going to hold the star analyzer grating up here. See all those lines? Those are spectra. In the center is the gas tube. And then going both to the right and left is the spectrum. Oh, and you can even see the spectrum from the lights on the ceiling at the top there. It's a little bit more messy because those light bulbs are wider. So that's all this does. And you just screw it onto your equipment, and then you get these rainbows that we study. So let me go and share my screen again, and we'll get back into the PowerPoint. So, and the star analyzer can be mounted on almost any equipment. So you can mount it on your DSLR lens cap. We have this little adapter here we sell, fits imaging camera. I've currently got one. We just started working on it. It's on a CDK-17 down in California at a remote site. So even bigger telescopes. You can use your DSLR on the telescope if that's the way you've done it before. Video camera. Now, it doesn't have to be a color camera. In fact, those of you who are imagers know that we get better images with mono. But I prefer to show color in my presentations because you'll see it's a little more intuitive in a moment. And you can mount it in a filter wheel. So almost any imaging equipment will work. Doesn't have to be video. It can be, of course, a static fixed image. Okay, so just a little bit of history to get us all to the same place. Sir Isaac Newton, we know that he was said to be the first person to split white light into its component colors with a prism. And you can also do that with a finely lined surface, even reflecting it off of a DVD or with a grating like the one I showed you a moment ago. Some of you may remember Bunsen burners from when you took chemistry. So Bunsen was a real pyromaniac, and he burned everything he could find, and he put it through a prism and he studied the results. And he learned an enormous amount about the kinds of things we're going to talk about tonight. Kirchhoff will talk about a little later. So I showed you this a moment ago, that each element has its own fingerprint, right? So hydrogen is so common in the universe that we've actually given those lines in hydrogen a name, and that is the Balmer lines, and even given them their own unique names, alpha, beta, and gamma. And this, for example, this hydrogen beta line, what color would we call that? Let's call that robin egg blue, okay? So that's the hydrogen beta line. We'll be seeing a lot of that. A quick overwhelming chart here. There's a periodic table showing all the elements and that they have different fingerprints. For example, hydrogen, there's that robin egg blue, hydrogen beta, that just doesn't exist over here in helium. So that's the last of the chemistry table we'll be looking at, though. So what do the astronomers that I've talked about so far all have in common? They're old white men. So there's lots of other people who have contributed to the field and upon whose shoulders we also stand. And I thought I'd mention some of them tonight in the context of spectroscopy. Annie Jump Cannon, you may recall, she and her team of computers were forbidden from using the Harvard telescope some years ago, more than a century. You can see them here studying glass plates. These are the plates, the spectroscopic plates that came off of the telescopes, and they studied over 400,000 spectra, and immersing themselves and saturating themselves in that spectra collection meant that they could evolve a stellar classification system that has been very valuable to us. Priyamvata Nataraja, she's at Yale. She studies black holes. Nancy Grace Roman was the first astronomer at NASA. Imagine the challenge in the late 1940s being a woman and being in that role. She did it really well. Of course, there's a telescope that's been named after her now. Jedediah Eisler was from Dartmouth, studying hyperactive black holes. And finally, Elisa Quintana studies exoplanets going around cooler red stars. What would it look like if you lived on a cooler red star? It might look like that, right? Because the predominant light is red, the plants are all going to evolve to be red, to absorb as much of that color as they can. So, okay, enough about theory, history, equipment. What can we actually do? That's what we're all here tonight for, right? So here's what I'd like you to come away with today, just really quickly. I know better than to read bullet points as much as I'd like to. And that is, I've already mentioned that it's a way to grow. It's easy to understand, and you can capture spectra easily. $200 grading in my software, it's about $100 is all it costs. So one good eyepiece and you're in for years worth of observing. And the thing I haven't mentioned yet is that it's much less susceptible to light pollution. So when we're doing like the kinds of imaging that we always do, you know, we're looking at fine gradients and, you know, how smooth the transitions are and sharp the images are. None of that matters to us. And I'll show you why in just a moment. So these stars do have life stories, and we can actually read them with a tool like this. So how do we do that? When we put the star analyzer on our telescope, there's the star, there's the starlight going through the grating and going down to our CCD or camera sensor. Now over here we can see that rainbow that came out of the prism. And so that's technically how we're producing this. Now, whether it's a prism like I just misspoke or a star analyzer, the result is pretty much the same. So here's a really amazing spectrum captured on a, let's see what it was, 8-inch Newtonian by Torsten Hansen. Each of these is a separate spectrum captured at different times. This axis is in temperature order. So the cool M stars are down here and the really hot B stars are up here. What does this establish? What did astronomers 130 years ago do when they saw this? They went, wow, each star temperature type has a different signature, right? It's telling us something about the composition of the star. So just two examples from this screen. One is that big gap. That's only visible on these cool stars over here. That, and I'm going to tell you everything I know about it. And the reason I'm, saying it that way is I don't want you to think, oh my God, now I have to understand what titanium oxide is. All I know about titanium oxide that produces these lines is that it's a molecule, and that on cool stars, it doesn't get burned up. Now, if I want to know more, because I have one of these spectra in my hands that I captured or on my screen, then I start reading, and reading makes sense to me. It's not some abstract concept. It's like my data. Okay, I probably beat that dead horse enough, but let's keep going. One other example, and that is this line here. It's a gap rather than a bright spot, but notice it's the strongest right here on this A star. And what's the color in that region? That's that robin egg blue. That's that hydrogen beta line. And you can see they don't even exist down here on the cool stars that we can see. So what's happening here? Just again, a 10-second review of things we may have studied in school. And that is the Bohr model has electrons going around in orbits around the nucleus of an atom. And those orbitals or orbits are numbered. And when an electron jumps from orbit 2 to orbit 4, it creates this line. And for some reason involving temperature, it happens on these stars up here, but not on these stars down there. Okay, so that's a really good survey of the kinds of things that we can do. So here I just wanted to backtrack a moment, and that is that I started by talking about gaps, and then I showed you some that had bright spots. What's the difference? Well, they're always going to be at the same spot in the same color. But that guy Kirchhoff, who I skipped a while back, talked about why this happens, why sometimes we get absorption lines and sometimes we get emission lines. It has to do with the temperatures of the clouds, the light's going through. We won't get into any of that. We're going to see examples of both of them here. Okay, Now, suppose the Hubble Space Telescope people made a huge mistake and they gave me telescope time. I don't deserve it. And then I said, I see a little gap, a little dimming there. And then I wrote a paper right in the Robin Egg Blue. We're familiar with that now. We sort of know that's hydrogen bomber. That's not enough to write a paper, right? We have to get quantitative. And how do we do that? Well, to do that, we take this graph, or excuse me, this image, and we plot the intensity. There's that little gap there. And here we can see an intensity plot. So this peak is because it's really bright in there, right? And this thing over here is because this starts out dim in this area. I'm not a great pointer, and gets dim over there. And that little barely discernible gap is shown right there. So now we can do science. We can measure the depth of it, its position, what color, all of these interesting things. Compare it on different telescopes, different nights. Watch how things are changing in the stars. So how do we get that graph? So my story is about 15 years ago, I wanted to get that graph. And I got a star analyzer like Grady, and I downloaded, actually, I went out in the backyard right outside the Venetian blinds there, here in Seattle, downtown, 3 miles from Pike Place Market. And I set my C8 up. I used literally a Logitech webcam. I just don't know a lot about this hardware stuff. And I had 2 star diagonals like attached to each other to get enough back focus. And some of you could explain to me why I had to do that. And I captured a video. And I came in that night. I had grass stains on my knees because I was looking at Vega in August. And the next morning, I tried to create this graph using the freeware that was out there, and I couldn't. It kept crashing. It was from France. It kept crashing, and to add insult to injury, when it crashed, the error messages were in French. That software's gotten a lot better, and I'm friendly with the author now. But at the time, I decided next weekend, I'll slap something together to create this graph. Take me a few hours, and it just took me a few hours to get the graph you're seeing here. And this is my original image. And now, 15 or 20,000 hours later, I'm almost done writing the software. It's never done. And I know better. I know it's evening there. And if I was to give you a long software demo, if any of your mics are enabled and turned on there, I'd start hearing people's heads crack on the microphones as you fell asleep, right? So I'm not going to give a long demo, but I want to give you a short one because I think it's important that you see how easy it is to do. Look, nobody wants to learn new software, right? So let's take a look. So there's my image. And this is a color image, as I mentioned. It could be a fit file. It could be, I haven't figured out why sometimes we call them fit and other times fits. By the way, they say it's the most widespread used standard in all of imaging or photography ever, because all of the astronomers are using it. And the reason it's been so successful and had such longevity is they can change it in time. They can add additional features and capabilities to the FITS file format. So there's my star and there's the spectrum. And maybe you can see that there's a little gap right there. Now, this is a still frame from that video from the first night. And let's move these sampling lines around our data. So we just look at that one region. And now over here, we have that graph. Let me drag that out of the way. There we go. So that peak there, as we saw earlier, is because the star is very bright. This is an intensity scale here. And this data over here, well, you see that big dip right there? That's the dip I mentioned right there. Okay, big deal. We've got a lot of dips here. Who cares? So, and how do I know what they are? Well, most of the time as amateurs, we're referring to books that have been written for us, and we're looking at things that we pretty much expect what we're going to see. And this is Vega, and this image has some very deep lines, and we know from the books that advise us on this stuff that we should look for these hydrogen bomber lines. So when I check this box, the software is going to add an overlay. We're more than halfway through the demo. Stay awake. Come on, wake up. We're going to see an overlay here of where the hydrogen bomber lines are. Now, I doubt you can read that because I didn't do my prep right. So let me go over to another screen here quickly and increase the font size of those hovering little definitions so you can, well, it didn't do it. Oh, I increased the wrong thing. All right, so much for showing you how easy the software is to use.
You're on a
But,
2-foot screen. We can see the numbers just fine.
oh, okay, good. Thanks, Matthew. So there you can see these are the bomber lines, and everywhere this overlay tells us to expect to see an absorption line, we're seeing them. We've now detected the hydrogen on Vega with an 8-inch telescope near downtown Seattle, and you could do the same thing. So I just want to show you one quick thing here. This is a video. I'm going to just start playing it back, and you can see the star is jumping around. In fact, let's just zoom in on the star so we can see our seeing was not great that night, right? Just the atmosphere is distorting the star, and so our data is jumping around too. Um, so that's pretty much all I wanted to show you in the software. As we leave the screen, I want to just ask you to, in your mind's eye, just remember that display where we can see the bomber lines overlaid on a spectrum, because we're going to come back to that. Okay, let's come back to our show here. And again, just a quick slide here to show you that the stars and Pleiades all have different looking spectra. Some have double peaks, some have emission lines, some have absorption lines. So that's the kind of variety we can see out there. And this is my software running. This is the screen I normally give the little demo on, but I forgot the screen was here. But this gives me an opportunity to just mention, if you're a teacher, that we have this, again, lack of preparation will get you every time, right? What a mess. I've got a little camera here. The mess that I'm referring to, I might not have held up high enough, but this is what cables do to you, right? So here's a little camera, little tripod mounted camera. I'll just dump that all over here that classrooms use. We have thousands of these out in the field. All the Ivy League schools have them, and homeschool. I mean, just all sorts of people are using these things. Okay, here's a star party in France, and you can see you wouldn't want to do this in a dark sky site, but here's a gas tube with its emission spectra they're showing. I just think it's fun to see that you can do this thing outdoors. And I wanted to mention that I know some of you in the club do outreach, and I want to thank you and encourage people to think more about doing more if you haven't done any. It's incredibly nourishing to give back and to help people learn about the stars. And it's easy. And this is just another tool in your toolkit. And just to finish up this little marketing spiel, if you're interested, oh, I think I have, I'll wait. We're going to have a slide on that in a minute. Okay, so here's our beloved, they're all beloved to us, right? Especially when we know their stories. M57. Now, when we look at that integrating, we see just the object twice because there's really only two emission lines on that object, hydrogen alpha and the oxygen. So this is pretty much the only extended object that is interesting because as they get bigger and bigger, the spectra get more and more difficult to get good resolution. And that's where these devices come in. So I had a friend who was working on a Porsches. He was a mechanic in a Porsche dealership some years ago, and he said, and it relates to what we all do. He said on the wall of the dealership showroom, they had a sign that said, "Speed costs money. How fast do you want to go?" And, really, it's the same thing with astronomy. Not only are these expensive, but they're really tough to use and learn how to use and what the data is they're giving you. Nobody really starts with devices like this. Even the DIY ones that are out there for $500 to $1,000, $500 to $1,000, it's just a little harder to learn out of the box with those until you've done some spectra. But once you have, then M42 looks like this. Even though it's an extended object because you have a slit on your spectroscope, you can see features like hydrogen and oxygen. This, of course, is the birthplace of stars, as opposed to M57 that we saw a moment ago that is more or less a graveyard. Here's a cool example. This is Uranus. You can see this is done with a 4.5-inch refractor and a video camera. For those of you who are, have aperture envy and, dark sky envy, to see the kinds of information that this graph shows captured with this simple a gear is really mind-blowing. It was for me when I first learned that this was possible. So here's why you might want to do this. And again, um, remember the first image, if you're an imager, that you captured of the moon? If it was like mine, it was overexposed. It probably wasn't focused well, but it was still the most beautiful image that I'd ever seen of the moon. And I showed it to my wife and my friends and my coworkers. And that's the kind of thrill that I was looking to recapture. And spectroscopy's done that for me. You get to do some science and it's not expensive. And I've beat this one far more than I need to. You own the data. You don't need dark sky sites. You don't need to have a PhD. Listen, if a knuckle dragger like me can learn this stuff, so can you. And again, really short images. Think about that video I just showed you on bright stars, not all the dim ones, but on the thousands of bright stars that are available. You can shoot a video, which means your frame rate is at least, a second or a half a second for each frame. So you're capturing data without having to sit around for hours. Um, and I'm not a DIYer. I break pretty much any hardware I work with. Look what I did with those cords a minute ago. So, you know, one of my favorite keys in Windows is the Control Z, the edit undo key. And you can't usually do that with hardware, unfortunately. No, nor can you do it in life. Wouldn't it be great if we could do a Control Z in life sometimes? So, and this I started to mention a moment ago, you can do really amazing outreach. And you can also mentor students. And I have a slide on that. And I'm currently mentoring a student in New Delhi, and we just finished up with a student in Ogden, Utah, who went to the International Science Fair this year. So there's lots of opportunities for you to tutor people. And so what I would say about what I'm talking about is spectroscopy opens the door into the classroom. Most of the time, what we all do is we're outside on the football field or at our dark sky site or at a park in the city on first quarter. But with spectroscopy, you can go to a chemistry teacher with a few months worth of playing around with it. So you have a few riffs about what's going on. And if you don't mind admitting, I don't know, which I admit far more often than I wish I had to, you can go to a chemistry teacher. They're teaching this stuff, this exact stuff. Orbits and electrons jumping, they can't avoid it. Physics teachers too, astronomy teachers too. You can go into their classroom. You can either give a talk like this, or you can get gas tubes like the one I showed you at the beginning, and you can show the spectra in the class. And then that night or the next clear night, next scheduled night, you can go out and show people that. That really excites students and it excites educators, whether it's a professor or a teacher at high school. And you're likely to find a student who says, I'd like to do more if you make yourself available. And then you've got a mentorship going, which is so incredibly rewarding. You can change somebody's life. Yeah, and I paused between those words because it's true. And it's such an amazing opportunity that you have with this kind of tool. Okay, so you can see here very briefly, we've in 1881, Henry Draper observed a comet, and the New York Times thought it was important enough to report. And here it is. If Hank can do it, so can we. So this was captured. You can see here in the original image over there is a string of gems. Look at the equipment that he used. Nothing, something tiny. It's a compact comet. Sorry if I bumped the mic there and you heard that. It's a compact comet, so we don't need a slit to observe it if you're trying to keep me honest here. So there's a string of gems. There's the Swan band emission lines. And that's pretty cool to do. This was captured by an astronomer in Rajasthan named Vikrant Agnihotri. Okay, another example of a comet. You can see here there is the sodium lines. Just another example I thought I'd show. Now, this is really pretty cool. So anybody who uses a C-clamp on their telescope equipment is my kind of observer, right? My problem would be I would tighten that thing down and I'd collapse the camera that it's holding. Like I said, I'm not a hardware guy. But what Robin Leadbeater did was he attached a star analyzer right on the nosepiece of a video camera, and he pointed it at the sky in August, and he observed the spectrum of Perseid. So this is the Perseid moving right here in that direction during the course of that image, that frame. And this is the spectrum. And right here, there was some sort of bright outburst. And over here, when we plot it, we can see he detected certain minerals in that comet. So that's pretty esoteric, but it's so cool. I really wanted to show it to you. We're not going to talk about the sun. We've all had enough of the sun in so many ways. But spectroscopy can be done during eclipses. So just to review for those of you like me who had sort of forgotten how it worked, Doppler shift. When something's moving towards us or away from us, its pitch changes, which is why when a car races past you, when you've stepped off that crosswalk downtown and it's got its horn on the whole time, how's it sound? Right, higher coming towards you, lower moving away. Same thing happens with light. So if we're looking for this triplet, I love that word, self-defining more or less. If we're expecting that triplet on a star, and instead we find it over to the right there, we know, like the car's horn, that light has been shifted and it's red shifted. The object's moving away from us. And the same thing if the light is shifted the other direction. Let's look at a real quick example. This will be the shortest description of a particular type of supernova you've ever heard, if I do it right. And that is there's two normal stars in a binary pair. One's bigger than the other. Some of its gas gets pulled down to the smaller star and it explodes. Less than 10 seconds, right? So there's, of course, lots more to supernovae, and this is just opening the door for you to observe them. Let's take a look at this supernova here. There it is in M101, brighter than all of the stars in the galaxy for a few days. So it's the end of this star's life. So I want to show you a little video of a supernova. This is just an animation, right? Not real data. But you can see that shell expanding. And that's what's going to be glowing that we're going to detect. So over here, just another, this is actually an image of a different supernova from a real telescope. And you can see it. There's that shell, right? So if we look over here at the spectrum from a star analyzer, this spectrum was captured by David Strange on just a 9-inch telescope. Now, again, this is a little bit dimmer of an object, so he captured 30 25-second images and combined them. And that gap right there shows up as this dip. So what meaning does that dip have? Again, we know what we're looking for here. Now, this next slide isn't going to be on the quiz, but I wanted to show you for different types of supernovae, right? Here's type 1a that we're looking at. There's a big dip right here, which they say is ionized silicon. That's all I know about it, except I know it should be at approximately this wavelength. So let's, now that I shut my slideshow down, there we go. So let's look at, in fact, why is my software still bleeding through that? Let's come back to the slideshow. There we go. So if we look at this wavelength, not only have we detected a supernova, but we can measure how fast that shell is coming towards us. Watch this. One addition, one multiplication, one division. Let's go past that slide again. So how fast is that shell expanding? Well, let's measure down here where that dip is. And that's at, 6150 as I call out there. So let's put that up here. Now, what if we burnt silicon in the lab? Would it be at that wavelength? Well, no, because in the lab, that Bunsen burner isn't moving away from us. So, and here the shell, away or towards, the shell is coming towards us. So that's been shifted. Here's what the wavelength would be if we burnt some sand in a lab. Those are different numbers because of Doppler shift. Here's the formula. I couldn't remember the Doppler shift formula. Wikipedia is our friend. To get how fast something is coming towards us, and when it's light, we just do this. So let's do that. We plug those numbers in, and now we can see the speed that supernova is coming towards us. There should be several wows here. One wow is, wow, that's fast. The other is, wow, I can't believe I detected that with a 9-inch telescope or smaller. So what's the significance of supernovae? Well, you may remember this guy. He won he and his team the Nobel Prize in 2011 for the research they did just before the turn of the century. They used supernovas as standard candles. And they detected the accelerating cosmological expansion, which is now coming into question. But he won the Nobel Prize. And you can duplicate the standard candle part. Listen, his telescope was worth a little more than $200, right? And whatever you paid for your telescope and camera. But bang for buck, we're doing pretty well with, $3,000 worth of equipment. So what about and he actually commented on the work that I'm doing. And if we get to that in Q&A, I'll mention it. So what about the spectrum of a black hole? Well, the thing is, a black hole's black. We're not going to see the black hole, but we can see the accretion disk as that material is getting sucked in by gravity. It gets hot. So here, everybody will recognize 3C273 from this image, right? Well, David Hayworth was kind enough to not only identify, but capture this image. And there it is. You can see in the spectrum, where is that? Over there. See, I've got a camera between me and the screen. I can't show you the camera because it can't take images of itself. But the camera is between me and the center of my screen. I want to be talking right to you, so I've got the camera there. But sometimes you may detect I have to peer around it. So there's the spectrum. And you notice we're into mono cameras here because, like in the previous image, mono's more sensitive and more accurate. Let's look at those two little peaks. There they are. Let's throw this into our software. There's the data. And now the cool thing. Martin Schmidt was in his 20s when he saw this image in his research lab. And he said, well, I want to know what these emission lines are, right? What these bright spots that we can barely discern are. So what's the first thing a scientist does? Well, they compare it to things they know. And what do we know? This is your mind's eye memory I asked you to hold on to of the Balmer lines. So if these were hydrogen lines, we'd expect them to line up with the reference lines. I don't think he used my software. It's a little before my time, but they don't line up. So he said, well, I guess they aren't hydrogen. I wonder what they are. But they were hydrogen, massively shifted. And I have a transcript of an interview with him. If you email me, I'll just send it to you, where he talks about making this discovery. Not so much the science, but the challenges, the digging, the going to his colleagues down the street. And my earbuds just died, so if somebody tries to talk to me, I won't hear them. So let me get some different hearing aids on. Just a second. Well, just don't talk to me. So we'll get back to that. Actually, bear with me. What a rookie mistake. I thought they were charged. So I'm going to stop there for a second. I'm going to stop sharing my screen. Here we can see that. Let me just change my audio device to my speaker on my computer. So all of you take a little stretch if you want while I go through this. And I'm going to put this. That's great. And I want this. Okay, I think I can hear you. Matthew, are you there? Can you talk to me?
I am. Can you hear me?
Well, if you're talking to me, I'm not hearing you.
Can you hear me?
So give me just a second here. Oh, I'm not
Testing,
hearing it either.
testing,
Hold on just a moment.
Testing.
Here we go. I got you. Okay. All right, folks, back to the show. Here we go. And we're in, and we'll come over to the show and pop it up. So he had to go to his colleagues and say, could this be true? And they sort of said, yeah, it sort of looks right. They're all shifted the right amount. But he was scared if he published it, it was so simple, somebody would figure out, he made a mistake, he'd be wrong, and so, but when he went home, and he describes this in this transcript, when he went home that night, he had a glass of wine, which he said, I never usually drink wine during the week. And his wife said, what's the occasion? And he said, something terrible happened today. She said, what? And he said, I made a big discovery, and we'll talk about the significance of it in a moment. I made a big discovery, and I'm afraid when it gets published, I'm going to be so popular that I'm not going to get to do my science. I'm going to be a celebrity. Now, if Kim Kardashian published this, she'd milk it for all it's worth, right? But as a scientist, he just wanted to do a science. It's a great transcript. Talks about the humanity, the humanness of this guy. So what is it about these that makes them so special? They're a long, long way away. And the fact that we can see them means that they're incredibly bright. And that was a new discovery, that we could detect something that was that far away. So, you know, I mentioned earlier that we can tease information out of light. And unfortunately, even if that light's 2 billion years old, we can tease light, if assuming light ages. It doesn't seem to age. Humans, not so much, right? This is Martin Schmidt a few years ago. He's since passed away. But it's interesting to see the difference and to see that young minds make those discoveries, usually in most fields. Some friends have accused me of throwing him under the bus, showing these before and after pictures. It's just I'm jealous of the guy. He's got a full head of hair. So this is the example I wanted to show you. This is the kind of thing that you could host people with. Now, doesn't matter what all these numbers are. We'd figure that out together if you wanted. But this is a high school student doing real science and winning science fairs and just changing their life. Okay, a couple more slides here and we'll be done. So, so far we've been looking at features like this. So this hydrogen alpha feature is how wide? It's about 50 angstroms wide. What if we want to drill down into that? Then we have to go to the high price spectrometers where we can see the same feature, that is this. And if we compare it to the moon, now the moon's not really moving towards or away from us very much, but clearly Vega is, because we can see some Doppler shift here and we can measure it fairly closely. So this is the last little demo for you. I've got a little demonstration aid. This is a star, right? And it's spinning very fast. So that means the light from this edge of the star is getting blue shifted as it comes towards you, and the light from this star is getting red shifted as it moves away from you, as it gets as if thrown off this spinning star. So here's a diagram of what that looks like. So the light is just shifted a little. So if we look at a star, unlike Vega, if we look at a star that's rotating very fast, this nice sharp dip gets really broad. And it's incredible you can do this. Both the previous example and this one requires one of those slit spectrometers. Okay, how do you get started? It's pretty easy. You need a star analyzer. I talked about that. You need some sort of camera, color, video, static, whatever. You need my software. These are the sharewares that are out there. This one's almost unlearnable without lots of commitment, even harder than PixInsight. And this is the French software. They're both French that I started with. And like I said, I'm friendly with the author, a woman named Valerie now. And the software is pretty good, but she's not really maintaining it much now. And you may need some sort of little adapters to get this mount right. There's tons of books out there. I'm not going to get into the details on all of these, except to tell you they're on my site. And I even recommend the one that you should start with there. We've got a very active forum, which you can post information, images on. This is sort of cool. AVSO has a database now that you can contribute spectra to for professional use. About 10 years ago, I gave a talk to about 100 AVSO members at one of their meetings. It was recorded, and the sample data is on our site. The software is free for 30 days. So tomorrow night or tomorrow morning or tonight, if you're a night owl, like most of us are as astronomers who are younger, I'm not a night owl anymore. You could download the data in the sample video, the tutorial video, and you could work through the examples one by one. And even if you never do this, you'd understand a lot. And if you open Sky and Telescope or Astronomy magazine or any of the astronomy magazines, and you look at the articles, most of them are going to talk about spectra. And that's why doing it, or at least understanding it, it can be so helpful. So there are opportunities for professional pro-am collaboration. Not as many as we'd like, but they're certainly possible, and hopefully more coming. So we've come a long way in the last 50 some minutes, haven't we? I know it's sort of like drinking from a fire hose. Remember those talking points I showed? It's easy. You can do it. You don't need a lot of equipment. You can do it in the city. And and it's inexpensive. There's some bullet points for you. So I want to thank you all for your patience, with not only my 50 minutes or so. Here's a slide from centuries ago. Fraunhofer. We mentioned Kirchhoff a little bit, but as I said, I want to thank you all for coming tonight and for smiling at a few of my jokes. I'm here to answer questions, not only until you all drag me off the stage. Matthew will get a crook and drag me off, but I'm also available online and via email and contact forms on our site. It would be my pleasure and honor to help you get started. Thank you all.
Open up the chats. Does anybody in the room have any questions?
We use the system with small smart telescopes that don't have a big aperture.
The question was asked if you could use this with small smart scopes that don't have a particularly large aperture.
That's an excellent question. I wish I could say yes. It can be done, but it's pretty tricky. It requires a special grading. And here's the big problem, ironically, that these automated telescopes make it harder for us to do spectra because the spectra can confuse its go-to capability. And spectra are a different brightness than the star that you're actually looking at. And the focus is a little different on spectra. So it's been done. I've done it. I wish it was easier, but it turns out it was going to be more of my time to support it. And I didn't think that it would be as popular. I know the S50s and the F30s and the dwarfs are very popular. In fact, if you're willing to take a Dremel tool and open up your S50, which voids your warranty, of course, you can actually use a star analyzer grading. But otherwise, it's not so easy to do. Also, the small aperture, they're pretty small. Anyway, that's a good question. And keep your eyes on our site. I'm not working on anything for them now. I mean, there are people who have accomplished this kind of thing. They've written software that hijacks the S50 firmware, and they play by their own acknowledgement cat and mouse with ZWO, and it's just it's too much. It's really for the super nerd, and I'm not that. Anyway, Ken, thanks for your comment. So that's my answer. Thank you for asking. And like I said, I wish I could say yes. I think that it would enable lots more people to get involved, but it's just not quite there yet. What else?
There ones.
So what is the easiest way to do spectroscopy with the star analyzer?
What is the easiest way to do spectroscopy with a star analyzer?
The easiest way would be if you're an imager already, and then it's likely you can just thread the star analyzer into your filter wheel or onto the nose piece of your camera. That's not a very definitive answer, but that's how easy it is. Now, it may be the star analyzer bends the light too much or too little. So we have a little calculator on our site where you plug in your camera specs and your telescope setup, and it tells you, yes, that'll work as is. I also often, not only often, but frequently, if that's more than often, frequently guys will email me or women will email me and say, here's my setup. What do I need? It's pretty easy. If you haven't done any spectroscopy before, again, you could get a ETX, a 6-inch telescope or an 8-inch SCT or a 4-inch refractor, a Skywatcher refractor. The telescope needs to be well corrected, if that's a term that some of you are familiar with. It has to have a low amount of chromatic aberration because we're imaging colors here. And so a less expensive telescope, especially trash scopes, typically won't work in that in this application. Is that a sufficient answer for you? Do you want to say something more specific? I'm happy to hear it out.
What about using a DSLR?
Absolutely. Gotcha. Sure. With a DSLR, what you do is, and I'll share my screen here for a second, if I can find the Zoom meeting. There it is. Let me just hit share. There's that share button behind the camera. There. So this is the DSLR link on our site. And that's the DSLR image of Orion's belt that I showed you earlier. So one thing you can do is if you have a DSLR, you pretty much need tracking. You can do imaging of spectra and stars without tracking, but you're chasing them across the sky. People have done that. But what we have this $40 little thread adapter that threads into the lens cap threads of the camera. It doesn't have to be a Canon. There are thread adapters and so forth. And this page discusses that. And that's where the star analyzer goes. And that Wolf-Rayet spectrum, no, I have a different Wolf-Rayet spectrum. I'll show you in a minute on our samples page, was done with a standalone DSLR. So if you have a DSLR, there's a close-up image of it. If you have a DSLR mounted on your telescope, we have this adapter for 40 bucks or so. It threads into your T-ring, and then the grating threads in here, and then these female threads go out to your telescope, however you have formerly were connecting it to here. So just with these adapters, and again, typically what I like to do is just have people send me their telescope model on our site, and we plug in the telescope and the camera model, and we confirm that the setup is right. Sometimes the grating needs to be on this side of the adapter to get it a little closer to the sensor, but it's a one-time setup. Just to show you that, here's that calculator I mentioned. Again, don't get put off by this. I often do this with people. There's the input that you put in, including the camera specs. And then if you get 3 green flags here, you're good to go. So that's the easiest way, I think, to get started with a DSLR. I like, of course, to control my DSLR with external software like Backyard EOS or Backyard Canon, that kind of software. So how's that for an answer? Any other questions that you have on that?
Nope, I think he's good. You had mentioned doing videos versus stills. What's the benefit to doing videos over stills? If you've just got a DSLR, is the juice worth the squeeze to have video?
That's a great question and a great analogy. I think video is helpful in the beginning because you get live feedback. But these days you can have your camera take an image every second and get as if live feedback. My software will load those images automatically. So I think these days the only advantage with the video, not really stacking, because my software doesn't stack very well. You can of course stack in AstroStackerd or some of the other Registax type programs, or even PixInsight, or there's lots of stacking programs out there. The biggest advantage with video is to have it live when I'm doing outreach. I like to have that flickering spectrum that I showed you in my software bouncing around. That color fill under the graph, really draws people in. They like, oh wow, here's something I don't have to look into a little eyepiece to see. What is it? It doesn't look like something I've seen before. So I think that for still images, of course, the advantage with still is you can get mono, and you can have longer exposures, and it's probably the way most of us are imaging today. But video will work too. The R in RSpec stands for real time. That's how I started with the video cameras. And I still use them when I go out to do outreach in schools. But it's a good question. What other questions?
A late admit. I will say I do want to make sure to
Okay.
thank you.
Sorry.
Spec is a sponsor for Astrofest that's coming up, so we do want to make sure to thank you for your participation in that. I know we've got some posters. You participated last year, so I would be remiss if I didn't thank you for that.
I'd forgotten all about that. I'm glad you reminded me.
Okay,
Yeah.
I'll bug you in a couple months. No worries.
Yeah,
Right.
here's the deal. Very few star parties actually reach out to me, and
Really?
I appreciate your persistence in doing that, and you're coming to me on a,
Okay.
on,
Okay.
on
Okay,
occasions. Somebody's not muted.
I got him.
Okay, on occasion, like at NEAF. By show of hands in the audience, I can see you all now. How many of you have been to NEAF? I'm curious. Not many. I know it's a long schlep up the East Coast. So maybe WSP. I went there years ago. Maybe I should take a junket down there and escape the rain here in Seattle next January. So I have given to clubs like at NEAF at conferences, star analyzer giveaways, but it seems sort of silly to me because not everybody wants to do this, and it's for somebody to receive this as a door prize and go, well, I'm not really an imager. I didn't feel good about doing it that way. So right now, what we are giving away just to show you. And let me just share my screen one more time. It's that periodic table of spectra. I think you can see my screen now. If you can't, let me know. So here is, oh, by the way, if you want to just sort of review some of the discussions here, this is a great interview by senior editor formerly at Sky and Telescope, Dennis DeCicco, great guy. But what I wanted to show you is this image. Most of you probably recognize Neil deGrasse Tyson. I wish I could say that he and I are best friends, but it doesn't quite work that way with celebrities, I'm afraid. I stood out on the pouring rain sidewalk for hours one night in Seattle to talk to him about spectroscopy. This will be a 2-minute story. I hope that you'll stay awake. I know you've got pizza coming in just a moment if it's not there already. I went down with a manila folder with some student spectra. There were 15 of us lined up on the sidewalk at about 11 a.m. when he came out from his meet and greet signing after his talk. People are coming up and fawning over him and, you know, getting autographs of the program. And then I come up and go, Dr. Tyson, I have these student spectra here of quasars. We're capturing quasar spectra. It was like he flipped the switch. He went from, at all times, a nice guy to being a scientist. I felt bad for the people behind me in line because now he wanted to talk science. You know, what aperture telescopes, how are you doing it? And then we were done. Then he kept signing for people, but he was still talking to me. You know, he's signing over here and he's talking to me here. And we were done. I said, well, thanks very much. And he said, can I have that manila folder? And I'm thinking, ka-ching, here it is. Neil deGrasse Tyson's going to endorse my product. So, of course, I gave it to him. I heard nothing. 2 years later, he's back in Seattle. Now I've got this poster that we created. I go down there. I've got the poster hanging out in front of me. He's walking towards his limousine. He says, there's about 12 of us behind the Jersey barrier. He says, it's too late. And we're all going, oh no, Dr. Tyson, just for a minute. So he sort of comes over and he looks up, he sees my poster hanging over the Jersey barrier, and he goes, that's brilliant, brilliant. Why hasn't anybody done that before? And again, I'm thinking, ka-ching. So then he says, can I have one? And my wife, in her wisdom, had sent me with a poster tube with a poster rolled up in it with my business card and a special piece of non-marring Scotch tape. And he took it. And then I said, on the spur of the moment, I said, and it was true, I said, Dr. Tyson, tomorrow I'm going out to an underprivileged high school and I'm going to do some solar spectroscopy with a hydrogen alpha telescope, a Lunt 100 millimeter. I didn't tell him that. And I said, would you like to join me? And you know, at first he said nothing, like he was thinking about it. He looked up and then he said, my dance card is filled tomorrow. And in fact, it was. 2 days later, I saw that he met with the Seattle Seahawks to talk physics on that day. But if he'd said yes, my next question, I realized, would have been, do you want to pick me up in your limousine or should we go in my 20-year-old Subaru Legacy? So he didn't say yes. And I went to see him one more time 2 years later in the rain outside. We had a cordial, nice chat. But I decided, and this will be the end of the story, I've exchanged some emails with him over the years. And, he's told me he just doesn't endorse products. And I understand that in his position. He was incredibly gracious and friendly, just like you see him on TV or in wherever on TV. What an archaic term. The thing I realized standing there was that I felt like a pauper standing outside the castle. And the king or queen are coming out of the castle, in their big stagecoach, and the paupers are lined up on the road, and they're just hoping that somebody will flip them a gold coin. And I'm embarrassed to admit, but that was my mindset. I was a marketer at that point, and I didn't like feeling that way. So anyway, long story short, I'm here today, and the poster is what I'm giving out at the Star Party. I'm donating to your Star Party. And I'd love to get down to it one of these years, but the poster will have to stand in for me. If you win the poster, I hope you enjoy it. If you've got kids, have them take it to school and show it to their chemistry teacher. There's thousands of posters out there in chemistry teachers' hands all over the world. All right, that was a long soliloquy. Go ahead. Anything else before we end this?
I see one final question. It looks like from the chat, and it asks, can the star analyzer help identify planetary nebulae?
Yeah, good question. It can, yeah, it can, in that you are able to, if we go back and look at our samples here, just again, I'm going to scroll through this quickly. You've seen some of these. This is, oh, there's the Saturn Nebula with the hydrogen alpha and the oxygen in my software. Here's a supergiant with emission lines. So yeah, you will see on emission nebula, you'll see two very distinct features. And the cool thing is you can drag, if there's multiple stars in your field of view, you can just drag my lines around here, this sampling box, and sample each star on the fly. So, of course, the video has to be playing for me to show you that here. Anyway, so yes, the answer is yes. Getting into the fine details of what the composition of that emission nebula are is a little bit more complex, but it's certainly doable. Good question. If you want more about that, just hit me up from our website.
Awesome. Well, Tom, thank you so much. I don't want to take up any more of your time than we already have, and we appreciate it so much. Thank you again.
My pleasure. Thank you, everybody. Have a great evening. And I'm the host, but I think I can leave without turning your meeting off. I hope that's the case. Thanks, Matthew. I appreciate all the work you did to make this happen.
Thank you, sir. Appreciate it. And then to any members that remain on the call or anybody in here, we do have a copy of the software. We do have a great a star analyzer in the club's possession. So if anybody wants to dabble in some spectroscopy, see me, see Richard, and we can probably arrange for that to take place. Let you play with it a little bit. We'll probably do it at Outreach coming up in the fall once we get going on that. But I think that's all I have. Everybody online, thank you for coming out. We'll see you next time.